let's start a topic called self-induction. What is this? Self-induction. We have discussed about electromagnetic induction, which is due to the magnetic flux change linked with a coil. Okay. Now the topic is self-induction. As its name indicates, it is the electromagnetic induction due to the self. What does it mean? Let's check it. See the definition of self-induction here. It is the property of a coil by virtue of which it opposes the growth or decays the current flowing through it. Opposes the growth or decay. It opposes the growth or decay of the current flowing through it. There's a lot of meaning behind this. So if you understand, so the meaning of this definition, the complete self-induction topic you will understand, right? And before that, this is the self-induction. See, it is the property of a coil, right? So each and every coil you take, it will have a property called self-induction, and it is also called as inertia of electricity. What is it called? Inertia of electricity. Alright. So what is this and how it is called inertia of electricity? We'll discuss by understanding this one. And before moving into this, let's have a look at this definition. If the current in the coil changes with time, imagine I have a coil in this way. I have a coil here. If there is a current flowing through this coil is constant, understand? So if there is a constant current flowing through this wire, what happens? There is a constant magnetic field associated with this coil. Yes or no? If there is a constant current flowing through the coil, constant magnetic field associated with this coil. For example, look at here. If I is constant, B is also constant, right? Is there any flux change linked with the coil? There is a flux linked with the coil, but there is no flux change linked with the coil. Understand? No flux change linked with the coil. As there is no flux change linked with the coil, there is no concept of induced EMF associated in this case. The same situation I can write in the other way. So where current is changing, look at here. This current is changing. The current passing through this coil is changing. The changing, it may be increasing or decreasing. The current passing through the coil may be increasing or decreasing, right? So now, magnetic field associated with this coil also will change, yes or no? 100% it will change. Now, here, if you really understand the concept here, when the magnetic field associated with this coil, which is having n number of turns, right, which is having these many number of turns, will keep on changes. The magnetic flux linked with the coil changes, right? So there is, instead of writing flux, see here, there is a flux change linked with the coil. Understand? So there is a flux change linked with the coil. When there is a flux change linked with the coil, so there is a production of induced EMF. What is that? There is a production of induced EMF. And this induced EMF always opposes the change in current. Will opposes the change in current. Okay. So this also we know by using the concept of Lenz's law. Lenz's law will tells us the direction of induced EMF, which will always try to oppose the change in the current. Okay. If the current value through this coil is increasing, this induced EMF will try to decrease it. If the current value passing through this conductor, through this coil is decreasing, the induced EMF will try to increase the current value in the circuit. Okay. Now, So this induced EMF will oppose the change in the current, and because of this, it is the induced EMF already produced. So this is called the self-induction here. What is it called? Self-induction. Why this is called self? Here, the induced EMF is produced due to its own flux change, yes or no? There is no other coil present here. Due to its own magnetic flux change, so there is an induced EMF is produced, so that's called the self-induction. Alright? Clear? Is it simple? It's so simple, right? So remember this flow, my dear children. Now read the definition in the blue color. If the current in the coil changes with time, see, this is the case. If the current in the coil changes with time, this is, you understand? The flux through the loop changes. Yes, there is a magnetic flux linked with the coil changes. See, the flux change linked with the coil. Hence, the induced EMF is produced. Yes, induced EMF is produced. This process is called self-induction, right? This is the process is called a self-induction. Okay, so this is the additional topic I have told you, which will connect you to this first basic definition of self-induction. Let's go back to the basic concept of self-induction, this one, right? So what is this? It is the property of a coil by virtue of which it opposes the growth or decay of the current flowing through the circuit, right? This is the most important and interesting part of the self-induction. Let's look at here. So simple. I have a coil. This is the coil. So there is a battery associated with this, and there is a plug key associated with this, right? This is called key. It's a battery of voltage V. So positive terminal and a negative terminal here. Look at the first case. First case, what I am doing here is key is closed. What happens when the key is closed? What happens when the key is open? Carefully listen. When the key is closed, slowly the current passing through the coil increases, yes or no? At a single instant, current passing through the coil will not increase. Slowly, at a single instant, current passing through this coil will not reach its maximum. Understand? Clear? At a single instant, because it is not a straight wire. Okay, it is a circular coil. Understand? Now, at an instant, it will instantaneously, the current value will not reach to the peak. Current value is slowly increases. When the current value is slowly increases, what happens? There is the magnetic flux associated. See, there is a magnetic field associated with this. Because of the current increasing, magnetic field associated with the coil. Due to the magnetic field associated with this coil, so that's what I am going to write. So B is also changing. When the magnetic field is changing, so there is a magnetic flux change is linked with the coil. Due to the magnetic flux change, so there is an induced EMF is produced in the coil, and look at here. This induced EMF will oppose, look at here, will oppose the growth of the current. Actually, the current is growing. Understand? So, will oppose the growth of the current. Actually, current needs to move to its peak value. But because of this opposition of self-induction, because of the opposition due to the self-induction, so there is a delay takes place. Delay in current to reach I max. I max means maximum value of the current. This is the part. This is the interesting and important part related to the self-induction. What is happening here? Because of the induced EMF, because of the self-induction phenomenon, so there is a delay in current to reach the maximum value. Because this induced EMF is opposing the growth of the current. Okay? Clear? Now, so look at this. When the key is open. When the key is open, current is finally reached to the maximum value. Imagine whatever may be the maximum, current is reached to the maximum value. Now, key is opened. Immediately current value will not become 0. Because this is not a straight wire, again I am telling you. Because this is not a straight wire, current value immediately will not come to the rest, will not come to 0 or a minimum value. Slowly the current value reduces. So whatever it may be, current value is decreasing here. Carefully look at here, my dear students. Current value is decreasing. So magnetic field associated with this also decreasing, but I am writing it as changing. Here also the magnetic flux associated with the magnetic flux change associated with the coil. This will produce induced EMF. So this is the interesting part here. This induced EMF will always opposes the change in current. Opposes the change in current. If the current is increasing, this induced EMF will try to decrease the amount of current passing through the coil. If current value is decreasing, listen, if the current value is decreasing, this induced EMF will try to increase the current flow in the circuit. Understand? So now look at here. This induced EMF will opposes, so the delay, or I can say decay of the current, will oppose the decay of current. So in previous case what happened? So induced EMF, which is called self-induction, which is opposing the growth of current, here which is opposing the decay of the current. Current is decreasing, right? This induced EMF is opposing decay of the current here. Okay. So now finally what happens? There is a, here also there is a delay takes place in current to reach I minimum or 0. Alright. Clear? So induced current and induced EMF will oppose the decay of the current, and finally what happens? There is a delay takes place for the current to reach the minimum value or 0 current. Understand? So this is how the self-induction concept is discussed, right? And let's read the initial statement, whatever we had written in the black letters here. Let's see. It is the property of a coil by virtue of which, the self-induction is the property of a coil by virtue of which it opposes the growth or decay of the current flowing through the circuit. So it is justified with this example. Alright. Now, so this is the reason it is called inertia of electricity. Inertia of electricity. Inertia means what? Inability to do something. Okay? Inability to do something. So the electric current is unable to reach its maximum value on its own because it is depending on self-induction here. If there is no concept of self-induction, directly it will reach to the maximum value. If there is no concept of self-induction, indirectly it will reach to its minimum value. There is no support is required here. Right? So that's called inertia of electricity. Electricity is unable to do something because of the self-induction. Right? Self-induction is a phenomenon, is also called as inertia of electricity. Alright? Clear? Now, look at here, my dear students. Magnetic flux associated with this coil is directly depending on the current. If the current value is more, magnetic flux associated with this definitely must be more. Okay. So what I can write? Magnetic flux associated with the coil is directly proportional to the current passing through the coil. Right? So from here I can write magnetic flux associated with this is equal to, there is a constant, that constant is called L. Right? So L into I. Understand? Imagine if there are n number of turns, see n number of turns, which is capital N. So each and every turn will be associated with flux change, magnetic flux linked with the coil. So n into phi, right? So the total number of turns into flux linked with it. So here I can write carefully, look at here, L is equal to n into phi divided by I. So you know what exactly this L is called? This L is called self-inductance. What is that? Inductance. Self-inductance is different. This is also called as coefficient of, what is this? Coefficient of self-induction. What is this? Coefficient of self-induction. This is also called as self-inductance. Self-induction is different and this is self-inductance. Okay, so this self-inductance and coefficient of self-induction formula is N into phi by I. From here you should understand. So the phi value is, so let me write somewhere here. So here L is equal to what I wrote, N phi by I, right? So N is number of turns, there won't be any unit, and this is Weber per ampere. So Weber per ampere is the SI unit of coefficient of self-induction or self-inductance. So now I can write carefully, you see. So this Weber per ampere is called Henry. What is it called? Henry. It is denoted with the symbol H. Henry is the unit of self-inductance or coefficient of self-induction. Okay, clear? So now here, if I value is equal to 1 ampere, if this I is 1 ampere, what happens? So your phi value is equal to L, right? There is a possibility of coefficient of self-induction is equal to the magnetic flux linked with the coil, right? When current is 1 ampere. And let's discuss more and more about self-inductance or coefficient of self-induction. What we have discussed is N into phi is equal to L into I. From here, L is equal to N phi by I. So remember this. This is the very important formula to find self-inductance of a circular coil and self-inductance of a long solenoid. Understand? To find these two derivations, this is the very important formula. What is this L? L is coefficient of self-induction or self-inductance. So I am writing here L is what? Coefficient of a self-induction or self-inductance. No confusion at all. Okay. Now, look at the thing. We know already induced EMF is equal to minus d phi by dt. If there are n number of turns, that I can write minus n into d phi by dt. The same expression I can write minus d by dt of n into phi. Anything when n is the n, anyway this n is number of turns associated with a coil or a solenoid, whatever it may be. So this is n, as it is constant it can come out, right? So the same thing like this. So there is no difference between these two expressions. Now, so this induced EMF is equal to minus d by dt of what is n into phi. From this expression, can you tell me n into phi? Just cross multiply. N into phi is equal to Li. Alright. So from here what I can write, it is minus L into di by dt. Look at the interesting expression for self-induced EMF. Right? What is that? Self-induced EMF, which is equal to minus L into di by dt. So where di by dt is rate of change of current. What is that? Rate of change of current. Di is change of current. Dt is rate of change of current. I am writing here. This di is change of current. This di by dt is rate of change of current. No confusions, right? Sometimes the questions can be asked change of current, sometimes question may be based on rate of change of current, right? You should not get confused. Now, so this negative sign is there. You carefully observe the negative sign. The negative sign is indicating that, right, always the induced EMF opposes the change of current. Induced EMF opposes the change of current. Okay. Every coil, wherever there is a self-induction phenomenon is taking place, that's called an inductor, right? You know, just for example, let me write, there is a conducting wire. So this we can represent by using a symbol called a resistor. Can I write like this? Each and every conductor will have some resistance. What this resistor will do? So because most of the students will have this common misconception, common misunderstanding between the resistor and inductor. Resistor will oppose the current. Just resistor will oppose the current. Understand? So this resistor, what it will do is, I'm writing here, so resistor will oppose the current. A very important difference I'm writing. Resistor will oppose the current. But what this inductor will do? Inductor is represented with this symbol. This is the inductor. Right? It's a coil. It is a solenoid. That is the inductor. So this inductor is represented with its inductance is L. Self-inductance. It is resistance. Right? See the similarity. Resistance and it is inductance. So this is called inductor. Understand? Inductor. So what this inductor will do, you know? This inductor will oppose the change of current. Inductor will oppose the change of current. So resistor will oppose just the current. Inductor will oppose the change of current. This is the difference you should understand. Okay. So now look at here. Induced EMF expression, we have got it as minus L into d phi by di by dt. Clear? Now, look at the interesting thing here. Imagine, let me draw three different diagrams here. So there is one diagram where current passing through here is 0. What is the induced EMF here? So induced EMF is equal to minus L into di by dt, as rate of change of current is 0 because current passing through it is 0. Right? So d by dt of current value is 0. It is not depending on time. It is just a 0. So this value will become 0. So the induced EMF will be 0 in this case. And now let's see. So there is a coil where the current value is increasing. Right? So the current value is increasing in this direction. Induced EMF, that means induced current will oppose this flow. So that is the induced current will oppose the flow. Understand? In detailed analysis we have done in the last slide. So as the direction of induced current is this one, you can write induced EMF direction also. So that is what? The induced EMF. That's called self-induced EMF direction. Okay. So this is the self-induced EMF direction in a coil where the current is increasing. Okay. So this value is equal to L into di by dt. So the negative sign is just indicating the direction. So direction, and it is also indicating the opposing the change of current. Now, the third diagram let me draw here. So where the current value is decreasing. So current value is decreasing, and opposite to that, so the direction of induced current is this one. So as this is the direction of induced current, so you can draw the induced current. Induced EMF, which is L into di by dt. Remember, L into di by dt. So you know, if the induced current direction is this one, generally current will be flowing from positive terminal to negative terminal. As it is induced, so this will be positive, this will be negative. Right? This is what we have discussed in Lenz's law. Okay. Clear? Now, let's move on to the topic called self-inductance of a circular coil. Self-inductance of a circular coil. Alright? Now, so you may get a doubt whether this inductor will have some resistance, because it is also a conducting wire. Yes, it will have resistance, but this resistance is a very, very low resistance. Okay, this will have very low resistance. Will not consider into the situation. Alright. So now self-inductance of a circular coil. So that L value we are going to find out. Now, let me imagine a circular coil of n number of turns, total number of turns n. You know the magnetic field at the center of the circular coil is mu naught n I divided by 2r. R is radius of the coil. Okay. R is radius of the circular coil. Magnetic flux associated with this is B into A, where B is mu naught Ni by 2R. Area is pi r square. Okay. Now, self-inductance. What is the formula for the self-inductance? I have told you here. This is the very important formula to be used to find the self-inductance of a circular coil and self-inductance of a solenoid. Alright. So now from here what I can write, L is equal to N into 5 divided by I. So N by I into 5 value. Magnetic flux linked with this coil whose number of turns are N. It is this one. So anyway, one R already cancelled here. Mu naught Ni into pi divided by 2. Okay, so I cancel. So L is equal to N square. That is mu naught. Also let me write first. So this is mu naught N into N square. So this is pi divided by 2. Mu naught N square pi divided by 2. Alright. So this is what the self-inductance of a circular coil, and one R is also there. See, mu naught Ni pi R by 2, mu naught Ni pi R by 2. So this is R, mu naught N square R pi by 2. Okay, so this inductance, self-inductance of a coil is depending on number of turns, radius of the circular coil. That means it is depending on geometry, radius of the circular coil. It is also depending on the number of turns. When the number of turns of the coil is increases, so then definitely the self-inductance of a coil also will increase. Now, the most important topic and most important question is self-inductance of a solenoid. So if the questions to be asked in your NEET exam and JEE exam, so it will be asked from this area. Remember, my dear students, right? If the question to be asked based on induction or inductance, so it will be mostly the most probable area of asking questions in this topic is from here. Self-inductance of a solenoid. So right now we'll do the self-inductance of a solenoid and followed by some other concepts and numericals. Self-inductance of a solenoid. So let me draw a solenoid here. So this is the solenoid picture. Solenoid, this solenoid is having capital N number of turns, right? And area of cross section is A. And if you carefully see, this is the solenoid is air core. There is no object or a metal rod which is present there. It is just air core solenoid whose permeability in free space is mu naught. Okay. Now, let us understand the self-inductance, and we know the self-inductance phi is equal to L into I. When there are n number of turns, it is n into phi is equal to L into I. So L is equal to, from here, L is equal to n phi divided by I. So this phi, what is this phi value here? This is what our aim is to find, okay? So this phi value is equal to B into A. So what is B? Magnetic field inside the solenoid, right? Outside the solenoid, magnetic field is 0. As this is a long solenoid, it's infinite. Magnetic field inside the solenoid is mu naught n into I into area of cross section is A. Listen carefully, where the small n is what? So I hope you could remember the concept called solenoid. So this small n is number of turns per unit length. So this small n is equal to capital N divided by L. So from here, so what is your capital N then? So small n into L. Okay? Clear? Now, let's look at this concept. Magnetic flux, you know. In terms of magnetic flux, in terms of capital N, let me write here. So magnetic flux is equal to mu naught, small n is capital N divided by L into I into A. Keep it here. Let's substitute this into our self-inductance. Self-inductance of a solenoid is equal to N into, N divided by I is here, okay, into phi. Phi value is mu naught N I A by L, okay. So gone. What is remained here? Mu naught N square capital A divided by L. The most important part is this one. Very important expression is mu naught N square by A. This is L of air core solenoid self-inductance, right? For example, instead of air presence, there is an iron rod is kept here, right? So the question is, find the self-inductance of a solenoid whose core is filled with iron, right? That's the question. In this case, the only thing changes is mu naught. Only thing changes is what? Mu naught. So, what is this? So, mu naught will become mu. Mu is permeability in a medium. It's not permeability in free space. It's a permeability in a medium. So, mu n square A by L. Right? But mu naught value, you know. Mu value we don't know. So for that, we know mu r is equal to mu by mu naught, relative permeability. From this, let us take, right? So from this, mu value will be mu r into mu naught. This mu is mu r into mu naught n square by A divided by L. So from here, L of iron, self-inductance of a solenoid which is not air cored, which is the core is filled with iron, which is equal to mu r into, if you really look at this equation, mu naught n square by A, n square A by L is this one. That is equal to the self-inductance of a solenoid which is air core. Okay, so remember this. Based on this also questions will be asked. Right? So that's it. So what we should understand here is self-inductance of a solenoid is depending on number of turns, area of cross section and length of the solenoid. Okay, number of turns, area of cross section and length of the solenoid. So it is depending on the geometry of the solenoid also. Okay, so geometry of the solenoid means what? It is depending on area of cross section. Clear? Now let's have a look at the numerical, the basic numericals here. A self-inductance of a coil having 200 turns. So how many number of turns? 200 is 10 millihenry. So the number of turns are 200 and inductance is 10 millihenry. Calculate the magnetic flux through the cross section of the coil. Corresponding to the current is 4 milliampere. Okay. First, calculate the cross section of the magnetic flux through the cross section. We have the formula N into phi is equal to L into I. So they are asking find the total magnetic flux associated with the coil. Total flux associated with the coil means the sum of the flux associated with each link. So we each coil, right? Each turn. So this is N phi they are asking initially, which is equal to L value is 10 into 10 raised to minus 3 Henry into I value is 4 into 10 raised to minus 3 ampere. So which you will get this one, 4 into 10 raised to minus 5 Weber. Alright. Now they are asking also determine the flux linked with each turn. This is for the total number of turns. Each turn, how you get? See, N phi is equal to 4 into something. So we need phi value which is equal to 4 into 10 raised to 5 divided by number of turns. How many number of turns? It's 200. So you get this answer. 2 into 10 raised to minus 7 Weber. Okay. This is for each turn. Flux associated with each turn. This is total flux associated with a coil. Okay. Clear? Let's have a look at the other question. If current in a 130 millihenry coil changes steadily from 20 milliampere to 28 milliampere. See, this if a current in 130 millihenry from 20 milliampere to 28 milliampere. Sorry, current is increasing. Current is increasing in 140 milliseconds. So all the data whatever is given, let me write L is equal to 130 millihenry and the current value are moving from 20 milliampere to 28 milliampere. That means change in current I can write it which is 8 milliampere in 140 meter per second. So that time is 140 milliseconds. Sorry, 140 milliseconds. Initially 0 milliseconds. Now at this point 0 millisecond. At this point 140 milliseconds. In this time interval, this is the change in current happened. Find the magnitude and direction of EMF, induced EMF. So simple, right? Induced EMF is equal to minus L into di by dt. If you want to find the direction, you need to keep negative sign. If they ask only magnitude, just the magnitude. Okay. So now E is equal to minus, what is L here? 130 into 10 raised to minus 3 Henry into di, 8 into 10 raised to minus 3 ampere by dt, 140 into 10 raised to minus 3 seconds. So if you find out, you will get the answer as minus 7.43 into 10 raised to minus 3 volt. Okay. So what is the minus indicates? Minus indicates this induced EMF will try to oppose the change of current. Here, the current is growing. What does induced EMF do? The induced EMF will try to delay the current to reach its maximum value. Understand? So that's called, this induced EMF opposes the change of current. Alright. Clear? So this is how the numericals also will be asked. So in this class, so you will be solving the assignment based on the simple basic numericals in this way. So you can also solve the numerical based on this. Right? So if you know this formula, mu naught n square A by L, if they give total number of turns, length, area, you can solve this question also. Self-inductance of a solenoid. Okay? And by using this also you can solve a question. And in the next class we'll solve some more problems related to the self-inductance and mutual inductance. The next topic is called mutual induction. Right? Next topic. And before that, so questions can also be asked from this. They are asking to find direction. This is the negative sign we have taken. Most of the times, E is equal to L into di by dt. From this, a lot of things you can find out. Lot of things. So E they will give, L they will give, time they will give, the change in time. So you need to find di, right? Di by dt they give, L you need to find out, and they'll give E. So like this kind of questions also will be asked. And most of the problems will be asked from here. L they give, N they give, I they give, you need to find phi, right? So write down the formulas. After every class, write down the formulas, whatever we have discussed. Then look at the options and look at the data given and use the appropriate formula, right? So that's it. Understand? So get ready for your assignment. All the best.